Yes, today we'll get ourselves introduced to the unit or the Unetformer. So Unetformer, it's a DL based model, that is deep learning based model, which is defined for the computer vision task, which is specifically for the semantic segmentation. So transformers, we already know what's a transformer and all. Let's look into what is a transformer and all. Yes. So let's go and deep dive into what a transformer is. From the course NLP, we already have the basic understanding of what a transformer is. Let's say we have given an input and this is a black box. We don't know what's inside it. Let's look into that further. And this is the output which we get. This is a type of black box. Here we have the layer normalization, then multi-head attention, multi-head self-attention, where we have many number of heads and we combine or concatenate those outputs from each head, and we follow the attention mechanism there for each head. We have query key value, 3 parameters for that, and then we again have the layer normalization, then MLP, the multi-layer perceptron. So mainly here we have the residual connections. Like let's say from the input we have the skip connections. Directly the input is given to this and added here. There's a concatenation and the same happens here. So this is a basic transformer architecture, but just the basic difference over here is this block. That is GLTB, the global local transformer block, right? So let's further understand what is GLTB and what's the basic understanding. But for now, this is a basic transformer architecture. Unit, what is a unit? We'll see. Then semantic segmentation is what? Like in the image classification, as we saw, for a whole image we classify like which label. Is it a building or is it a tree? It's a road. But here in the semantic segmentation, in an image, we divide an image into different number of segments, and in the segment we have many number of pixels. So for each pixel, we classify which label is that, right? So the goal is to classify every pixel into a road or a building, or which label is that actually, right? So this is a semantic segmentation. Remote sensing is what we capture through the satellites, okay? And then urban scene imagery is the roads or buildings or cars or trees or building rooftops, whatever it may be, the labels given. That is urban scene imagery. Fine. So the goal is, as we know, the main goal is to classify every pixel into the predefined labels, the predefined category, that is whether it's maybe a road or a building or a tree. So why it's so important is it has many applications like land cover mapping and environmental monitoring. So hence it's obviously important. Okay, let's come from the start. Traditional ML. So here in the traditional ML we used some support vector machines and random forest, but overall it didn't work out. What was the problem actually was it is not good at capturing some details of the images, like the features, the edges, or capturing some patterns or recognizing some patterns. It was not good at that. So traditional ML failed. Next comes the CNN, convolutional neural networks. It captures some fine details locally, not globally. Please mark this, it's locally. And it recognizes better patterns like edges or whatever it may be, but it recognizes better patterns locally. So yes, it was good at recognizing patterns and analyzing them. What was the limitation then? Why we had to switch to Unetformer? The limitations were it couldn't capture the global context. And also the long range dependencies. It only looks at the local regions. For the better understanding, let's say we have a pixel, okay? We have many number of pixels, let's say. Just assume that in an image. So for this image, I am predicting that which label is it. According to some color or some features, I predicted this label as a road. I have only predicted it using a local knowledge, locally, okay? But if you see the global scope, if you see it in overall view, it's actually a building rooftop. Now it fails, right? So the result goes wrong. That's not true. That's a wrong result. So CNN fails here. Next comes the transformer. As covered in NLP structure here course, now we shall see what is actually a transformer doing and how is it performing. Okay, so as it covers the local information but couldn't actually come to a large detailing. So we switched to this transformers where it was able to capture a good global context. But the problem with this was it was really computationally expensive, and also it's not suitable for the real-time applications which we have to use it in our daily life, but it was not suitable for the real-time applications. So transformer was discarded. Next comes the Unetformer. So in this Unetformer, we used the CNN encoder and the transformer decoder, where we combined both of these features and made it as a hybrid model. It's hence known as hybrid model because we took an encoder from the CNN and decoder from this transformer. Hence it's known as the hybrid model. So the Unetformer hence performs very accurately, and it's also lightweight and faster. Right? It gives a good accuracy, and it's also suitable for the real-time applications. Hence unit is good. Fine. What's the key innovation here? What's new in this Unetformer? GLTB. GLTB was the main thing. Global Local Transformer Block. So it has two branches. As we give the input, the image is divided into the global branch and the local branch, where here we use some attention mechanism for capturing the global context of a pixel, and also we have some window-based attention and cross-shaped interaction here. In this local branch, we use a convolution to capture some fine details. Okay, so at last we combine both of this and get the output, which results in a better segmentation accuracy, which we need. Fine. This is the key innovation, the new one. Then comes FRH, feature refinement head. It's added at the end after we get the output, which is to improve our feature quality and also to refine our input, the segmentation input which we have attained at the last. Now let's slowly get into the architecture thing. What's unit? Okay. So let's get into the part. So unit, by this name, it is called so because it's in some U shape. I'm just giving the overview. So it has mainly 4 parts. First one is encoder, second one is decoder, third is bottleneck, and the fourth is skip connection, right? So here in this part we have encoder, here we have decoder, and the lines between them, as you see in the architecture, is a skip connection, and here at the bottom we have a bottleneck. Let's get into the architecture slowly. Yes, let's deep dive into some architecture. So unit is called so because it's in a U shape, right? So here we have mainly 4 parts: encoder, decoder, skip connection, and bottleneck. If we divide this into 2, split it into 2, this is the encoder part, this is the decoder part, and the below one is the bottleneck. Then this is a skip connection, the gray color one, right? Okay, so the input which we commonly give is the image, right? So what is this representation? 164 and 64 is one is representing the gray color one, the gray glass, and this is the number of channels. Okay, we give the input image, and the dimensions of the input image which we give is 572 cross 572. That is the height cross width, like we commonly see in a PyTorch representation, B, C, H, W. That is batch, channels, and height and width, right? Okay. So here what is actually happening is the spatial dimensions are getting decreased and the channels are getting increased, right? Let's take an example to understand it better. Let's say we have given an input with the dimensions 572 cross 572 with one channel. Okay. And the output which we got was 28 cross 28 as the dimensions, the height and the width. If we observe, the spatial dimensions, these got decreased from 572 to 28. This is one being one channel, like channel in the sense it's the number of features, or one feature. The channels get increased. Let's say the number of channels being 1024, right? So this is the case. The spatial dimensions got decreased from 572 to 28, and the number of channels got increased, right? Okay. Next, so this is what is happening here. From 572 dimension, it slowly got reduced by 2. How does this reduce? It's by using convolutional filter. The blue arrow which we see now is 3 by 3 convolution layer. It's kind of filter. Like to represent it dimensionally, we have an input like 572 cross 572 into 1, that is channels. And this is a convolutional filter 3 by 3 by 64. This is a convolutional layer, that's a filter. And the output which we get after applying this convolutional filter is 570. It reduces by 2. Okay. Now the number of channels becomes 64. Initially it was 1. Channels got increased. The spatial dimensions got decreased. Got that? Okay. So now we have 2 convolutional layers here, and after that finally we got the dimensions as 568. Okay. But the channels were 64. The same 64 channels is passed on to this, the next level. Let's say this is a level 1, this is a level 2, level 3, level 4. This being the bottleneck. So this 64 being the same is passed on to the next one. So this one's number of channels are 64. Okay. And so now the spatial dimensions got reduced to half because of this max polling layer. We have seen this, which is, let's say if my height width was h comma w in the level 1, after applying the max polling layer, our height and width reduces to 2 because we have applied the max polling layer. Okay. No. So 568 by 2, 284. Then the spatial dimension decreases because we applied the convolutional layer. Then 280 again because we have applied the convolutional layer. The channels keeps on growing. Initially it was 64, but now it is 128. Next. Now this channel size being 128 is passed on to the next level, level 3. Now the spatial dimensions get halved. It was 280 divided by 2, 140. The spatial dimensions decrease as we are applying the convolutional layer, and the number of channels increase, that is 256. And then this 256 number of channels are being passed, and number of channels increase, spatial dimensions decrease. Okay, this is clear. Now coming to this bottleneck part, the same thing happens. This is where the encoder transforms to the decoder. As we have seen, this part is encoder, right? Okay, we have seen this one. This is where the downsampling happens, that is the max pooling, where the height and width keeps on reduces by 2, that is spatial dimensions decreases. And this is where in the decoder part upsampling happens. Okay. Now this one, the spatial dimension being 28, now our dimensions are increasing. But the part is, why is the color is different? This white part is the encoder and this one being decoder, because the decoder part upsampling automatically happens. Using this skip connection, we are concatenating an encoder part with this decoder. Got that? So this is happening, and the spatial dimensions of course increases because it is upsampling. Now the channels decrease, 1024, 512, 256, 128. Okay, so the same procedure, but the thing is skip connection. Just encoder goes on, concatenates with the decoder, and here we have upsampling. This is the one. Same number of levels are 4, 1, 2, 3, 4. But the thing you observe here is, after applying the convolutional layer for the channels being 64, 1 by 1 convolutional layer, the result was 2. Right? What was that? But initially we have 1, right? The input image being 1 as a gray class. The output which we got in the segmentation map was 2. What was it? It's like very similar to the binary classification. Let's say we have a dog and a cat. We need to predict the image whether it's a dog or a cat. The probability of the image being dog is 0.9 and 0.1. We get the solution for both, but we want any one of those. So that's the thing here. So yeah, this is the unit. It's called so because it's in a U shape. It has skip connections with those, so that this information rich level, this level 1 which is information rich, the actual information may not be lost as we are downsampling and upsampling. These skip connections are really useful. If you see ResNet, the residual net, the skip connections are really useful, right? And one more thing to notice here is copy and crop. Okay, in this copy and crop we are seeing this dashed edges. See, this dashed edges in the last one, in this last layer. What is happening here? Copy and crop, the layer being this length, it's being cropped. Why is it so? Let's say our image was of dimension 64 of 64 and a number of channels being 5 and 2, and the other one of dimensions 56 cross 56 and the number of channels being 1024. If we want to use a skip connection, these spatial dimensions must match, right? If these are different, we can't. So skip connection solves this problem. This is why we use copy and crop. Up convolution is okay, upsampling convolution layer which is used at the end here. Fine. And also we have seen how spatially our images dimensions get trunked, and also we have seen dimensionally how it goes. This is in the case of level 1, right? Let's see in the level 2 case. In the level 2 we have 284 as our dimensions. 284 cross 284, the channels being 64 which is passed on from the previous level. And also now we apply the filter convolution layer. 3 cross 3 by 128, the number of channels. What will be the output? 282 cross, the spatial dimensions must decrease, right? From 284 to 282. Now will it be 64 or 128, the number of channels in the output? Obviously it will be 128. Yes. Okay, and here one more concept in the bottleneck. Here one more concept is about bilinear interpolation. Bilinear interpolation, where our input is an image and output must be a masked one, where it defines some boundaries, a set of boundaries. Let's understand it mathematically. 1 2 3 4, dimensions being 2 by 2. For it to be in 3 by 3, after applying the interpolation, 1 2 3 4, after applying this interpolation it becomes 1.5, this one becomes 3.5, this becomes 2, this becomes 3, this becomes 2.5. This is a concept which is useful. Let's dive into the actual architecture from the paper, and this will be useful. After looking into the actual architecture, this clicks actually. Yeah. After going through the code and training the model, I have designed an architecture. So let me explain the architecture according to the code. Yes. Let's say we have an input X with the dimensions being B, 3, H, W. 3 because I have assumed the number of channels being 3 because the image is an RGB image, right? So yeah. Next, it goes through the ResNet 18. In the paper, the ResNet 18 is the backbone, that is the encoder, CNN encoder, where the downsampling happens and the number of channels increase and the spatial dimensions decrease, right? According to the one which we talked earlier. So that happens. This is this encoder part. I'm talking in the context of the code, the model which I have trained. I'm talking this in the context of the code. Yes, let's move. In the code, it's given after applying this, we get the output. The 4 outputs, rest 1, rest 2, rest 3, rest 4. And after this, the downsampling happens, right? Let's also indicate those dimensions for this. B, 64, H by 4, W by 4. Why is it so? Because we have a stride equals to 2 and convolution layer 7 by 7. Also the max pooling, that is 3 by 3, where our spatial size decreases by 2 due to the convolution layer, and due to the max pooling it again reduces to 2, hence it becomes by 4. Fine. Now here number of channels increase to 128, H by 8, W by 8. Here 256, H by 16, W by 16. And now here 5, 12, 32, 32. Okay. Now for this, taking this rest 4 as a input, I have applied convolutional VN layer where the batch normalization happens. Let's deep dive into the architecture of this convolutional batch normalization further. B, 64, H by 32, W by 32. The dimensions of this. And then this is sent to a block. This is just an overview of the architecture, because the code is really very detailed. Like each part has many things to discuss. So I'm just drawing the overview so that we actually know the whole architecture model. So after passing into the block, it's indicated as B4 in the code, but then we have modified it to the block as the initialization is done in the definite block. Now it's passed into the upsampling bilinear 2D. Upsampling bilinear 2D. And the output which we get is H4. Just remember this, H4. Okay. This being X in the previous layer, this X and the rest 3. Both of this are combined. That is, the fusion happens here. This is initialized as WF. Let's say the fusion happens here. And the dimensions being B, 64, H by 16, W by 16. You see, you observe the dimensions. It is very similar to the architecture which we have seen, but this is according to the code. As we have read the research paper, I am drawing it according to the code so that it is easy to understand. Next, this fused one is again passed to a block, and then upsampling is done. I am representing it as UP3. Let's say this is UP4, UP3, and this being B, 64, H by 8 and W by 8. And the output which we get is H3. Let's remember this. This one also, let's remember H4 and H3. If you observe, in this diagram we can relate to the skip connections in the previous diagram, and also after this we got the outputs, right? Rest 4. These are the encoder outputs at the each levels, like we had 4 levels before, and this is the decoder part which we are learning. Now, this one being X in the previous layer, let's again perform fusion. WF. Let's take this rest 2 and also X, perform fusion, and the dimension is same here. After performing the fusion, we also transfer it to a block where we get the, after upsampling we get the output like H2. Okay, H2, H3 and H4. Great. Now, assuming this as X from the previous layer, I am taking res 1 and this X and performing the fusion. But then this is FRH, okay, as we have seen in the earlier one. FRH being the feature refinement head, right? Okay, feature refinement head, and then we get the segmentation head. This one's dimension being, we had like B, 64, number of channels being this, and the spatial dimensions is reduced by 8. This one being 64, H by 4, W by 4. And then we interpolate as we have discussed. This is the X we got finally. And what do we do with these outputs from the decoder here? Okay, we concatenate easily. We take this H3, H4 and then H2, concatenate these and call this as AH, the auxiliary head. This is the output which we written from the code, that is, it gives us like return X, AH, and that is this X, AH. Okay, so this is a overview of the architecture from the paper. Yes, and more to discuss was about DLTB and multilayer perceptron, and also about block here in this block, this one. Let's see this. So this is the block one where we have input normalization layer and then GLTB block, that is the global local transformer block, and then the residual connection again repeats the normalization, multilayer perceptron, draw path, and then output. This is a batch normalization thing. And GLTB is this one. The input is divided into two branches, global and local, where we take the input and divide into the three parameters, that is query, key, and then value q, k, v, and do window partition. Let's come across this window partition a bit, and this one is pending it, and then self attention we know, window merge, and then this one also I'll explain. I think this is a bit confusing. GLTB, the input is given, right? This is divided into two branches, global and then local. Here in the global side we do window partitioning and thing. So the window partitioning is done. So this 1D sequence is divided into three, query, key, and then value. And from the attention mechanism we know, like QK transpose by root DK into V. We apply softmax here. We do transpose of these, right? So we do transpose of this and apply softmax, and also do the scaling, then combine it with, multiply it with the V. I mean, it's nothing but reshaping. And then cross-shaped window interaction, that is, let's say the image is divided into these four windows. The window not only takes the local information but also interacts with the other window so that it can get the wider context, right? So this is a cross-shaped window interaction, and hence we get the global context from here using attention mechanism. And this one, the local one, it is given as a 2D feature map, and then it's divided into two, that is 1x1 convolutional layer and 3x3 convolutional layer. We apply normalization and then concatenate. This is all also according to the code and also from the research paper. And output we get the local context. We sum both of these, combine them, and apply FRH, that is feature refinement head. Hence we get the nice output, not only the global and also the local context, which focuses on the local details. Now let's look into the window partitioning operation. Which we have it in the global context branch, the global branch, GLTB. So what do we do here is we apply attention on small windows instead of the whole image, right? So let's say we have an input of dimensions b, c, h, w, batch size, channel height and width. We apply a convolutional layer, 1x1 convolutional layer. This is like number of images and this is a features, okay? Yeah, convolutional layer, this adjusts the number of channels, and after that our image becomes this. This is not actually the exact one, this is just our imagination. So as convolution layer adjusts the number of channels, this C becomes 3C, as that is the RGB image. I have already said, like, RGB image has 3 channels. Okay, now window partitioning. This image is divided into windows. Let's say this is a window, this is a window, 4 windows. Okay, 4 windows. This is a local window, and each window has W by W dimension. Hence, what will be the dimension now for each window? B H by W, the width, the total width by W, into how many channels? 3, right? So size of the each one is W by W. Hence the dimension turns out to be this for each one. Next, after reshaping, so this is for each window, yeah. This is for each window, and after reshaping, this becomes a 2D sequence, and then we assign to each head to compute the self attention, like QKV, as we saw, QK transpose by root DK. So the output one will be B H by W, W by W. Each one is W by W, and then channels divided by H. Yes, this is a window partition. And next one is cross-shaped. Cross-shaped is capturing the vertical and horizontal info, right? If we have this pixel concentrating also on the vertical and also the horizontal one, where we take the average and sum of those both. Let's say we have this point, we have this point, we have this point. this this pixel not only focuses locally on this particular window but also interacts with the other window so that it gets the global context. This is the cross-shaped window context interaction. Hence we get the global context with this such a concept. And now the architecture part is finished. Let's come to the equations. From the paper equations part, we have feature fusion equation. This is a fusion feature. Alpha is like the weight which we need to give whether to the encoder, or we need to trust the encoder or the decoder. And RF, this is the encoder part, 1 minus alpha into GLF. This is the fusion feature equation. Second one being the cross entropy loss. Cross entropy, like what's the difference between the predicted and the actual one? Minus 1 by n summation n equal to 1 to n summation k equal to 1 to k, yk being the true label, y bar being the predicted one. So we take log of that, negative log likelihood. Okay, then this is a cross entropy equation, fusion feature equation. Self attention, we have already seen this. Query, key, value. We apply the softmax after multiplying the query and key transpose and scale it, then multiply with value vector. Fourth one, cross window interaction. This one, we capture meaning from different windows, that is horizontal and vertical pooling. P1 of m comma n, let's say this is a point. Sum it from the horizontal one, info which is coming from one window, d1 di and p1, dj, this is from the neighbor window, p2 by w, we average it. If it's only 2 in the numerator, by 2. Okay, then that's it. These are the equations. These are the results after training on the two data sets, that is Wehingen and Potsdam. These are the results. These are the labels like impervious surface, building, low vegetation, trees, and then cars. This is the matrix MIOU. Measures the overlap between the predicted and the ground truth labels. This is F1, that is harmonic mean of the precision and the recall. Overall accuracy. Overall accuracy is consider the pixels irrespective of their class labels. Right. This is how we got 92.17, 85.8. And coming to the Potsdam dataset, these are the results.